Sediment transport is the movement of solid particles, typically due to a combination of gravity acting on the sediment, and/or the movement of the fluid in which the sediment is entrained. Sediment transport occurs in natural systems where the particles are clastic rocks, mud, or clay, the fluid is air, water, or ice, and the force of gravity acts to move the particles along the sloping surface on which they are resting. Sediment transport due to fluid motion occurs in rivers, oceans, lakes, seas, and other bodies of water due to currents and tides. Transport is also caused by glaciers as they flow, and on terrestrial surfaces under the influence of wind. Sediment transport due only to gravity can occur on sloping surfaces in general, including hill slopes, scarps, cliffs, and the continental shelf continental slope boundary. Sediment transport is important in the fields of sedimentary geology, geomorphology, civil engineering and environmental engineering. Knowledge of sediment transport is most often used to determine whether erosion or deposition will occur, the magnitude of this erosion or deposition, and the time and distance over which it will occur. Mechanisms. Aeolian or aeolian is the term for sediment transport by wind. This process results in the formation of ripples and sand dunes. Typically, the size of the transported sediment is fine sand and smaller, because air is a fluid with low density and viscosity, and can therefore not exert very much shear on its bed. Bed forms are generated by aeolian sediment transport in the terrestrial near-surface environment. Ripples and dunes form as a natural self-organizing response to sediment transport. Aeolian sediment transport is common on beaches and in the arid regions of the world, because it is in these environments that vegetation does not prevent the presence and motion of fields of sand. Wind-blown very fine-grained dust is capable of entering the upper atmosphere and moving across the globe. Dust from the Sahara deposits on the Canary Islands and islands in the Caribbean, and dust from the Gobi Desert has deposited on the western United States. This sediment is important to the soil budget and ecology of several islands. Deposits of fine-grained wind-blown glacial sediment are called loess. Fluvial in geology, physical geography, and sediment transport. Fluvial processes relate to flowing water in natural systems. This encompasses rivers, streams, periglacial flows, flash floods, and glacial lake outburst floods. Sediment moved by water can be larger than sediment moved by air because water has both a higher density and viscosity. In typical rivers, the largest carried sediment is of sand and gravel size, but larger floods can carry cobbles and even boulders. Fluvial sediment transport can result in the formation of ripples and dunes, in fractal-shaped patterns of erosion, in complex patterns of natural river systems, and in the development of floodplains. Coastal sediment transport takes place in near-shore environments due to the motions of waves and currents. At the mouths of rivers, coastal sediment and fluvial sediment transport processes mesh to create river deltas. Coastal sediment transport results in the formation of characteristic coastal landforms such as beaches, barrier islands, and capes. Glacial. As glaciers move over the beds, they entrain and move material of all sizes. Glaciers can carry the largest sediment, and areas of glacial deposition often contain a large number of glacial erratics, many of which are several meters in diameter. Glaciers also pulverize rock into glacial flour, which is so fine that it is often carried away by winds to create loess deposits thousands of kilometers afield. Sediment entrained in glaciers often moves approximately along the glacial flow lines, causing it to appear at the surface in the ablation zone. Hillslope. In hill-slope sediment transport, a variety of processes move regolith downslope. These include soil creep, tree throw, movement of soil by burrowing animals, slumping and landsliding of the hill slope. These processes generally combine to give the hill slope a profile that looks like a solution to the diffusion equation, where the diffusivity is a parameter that relates to the ease of sediment transport on the particular hill slope. For this reason, the tops of hills generally have a parabolic concave up profile, which grades into a convex up profile around valleys. As hill slopes steepen, however, they become more prone to episodic landslides and other mass-wasting events. Therefore, hill slope processes are better described by a nonlinear diffusion equation in which classic diffusion dominates for shallow slopes and erosion rates go to infinity as the hill slope reaches a critical angle of repose. Debris flow. Large masses of material are moved in debris flows, hyperconcentrated mixtures of mud clasts that range up to boulder size, and water. Debris flows move as granular flows down steep mountain valleys and washes, because they transport sediment as a granular mixture. Their transport mechanisms and capacities scale differently from those of fluvial systems. Applications. Sediment transport is applied to solve many environmental, geotechnical, and geological problems. Measuring and quantifying sediment transport or erosion is therefore important for coastal engineering. Several sediment erosion devices have been designed in order to quantify sediment erosion. One such device, also referred to as the BEAST, has been calibrated in order to quantify rates of sediment erosion. Movement of sediment is important in providing habitat for fish and other organisms in rivers. Therefore, managers of highly regulated rivers, which are often sediment-starved due to dams, are often advised to stage short floods to refresh the bed material and rebuild bars. This is also important, for example, in the Grand Canyon of the Colorado River, to rebuild shoreline habitats also used as campsites. Sediment discharge into a reservoir formed by a dam forms a reservoir delta. This delta will fill the basin, and eventually either the reservoir will need to be dredged or the dam will need to be removed. Knowledge of sediment transport can be used to properly plan to extend the life of a dam. Geologists can use inverse solutions of transport relationships to understand flow depth, velocity, and direction from sedimentary rocks and young deposits of alluvial materials. Flow in culverts, over dams, and around bridge piers can cause erosion of the bed. This erosion can damage the environment and expose or unsettle the foundations of the structure. Therefore, good knowledge of the mechanics of sediment transport in a built environment are important for civil and hydraulic engineers. When suspended sediment transport is increased due to human activities, causing environmental problems including the filling of channels, it is called siltation after the grain size fraction dominating the process. Gjellström-Sundborg diagram. In 1935, Philip Gjellström created the Gjellström curve, a graph which shows the relationship between the size of sediment and the velocity required to erode, transport it, or deposit it. The graph is logarithmic. A.K. Sundborg later modified the Gjellström curve to show separate curves for the movement threshold corresponding to several water depths, as is necessary if the flow velocity rather than the boundary shear stress is used for the flow strength. This curve has no more than a historical value nowadays, although its simplicity is still attractive. Among the drawbacks of this curve that it does not take the water depth into account, and more importantly, that it does not show that sedimentation is caused by flow velocity deceleration and erosion is caused by flow acceleration. The dimensionless shields diagram is now unanimously accepted for initiation of sediment motion in rivers. Much work was done on river sediment transport formulae in the second half of the 20th century, and that work should be used preferably to Gjellström's curve, e.a. Meyer, Peter and Amp, Muller, Engel and Hansen, Lefort, Beludi.